Keep. Okay, 16.7 today. Or sorry, 16.6 actually. Let me go back to 16.6. There we go. Okay, 16.6 is parametric surfaces and their areas. Okay, so we have some sort of surface. We want to talk about the surface, parameterize this surface. Maybe it's like a globe or a cylinder. I don't know how you want to think about it. But we have some sort of surface and we want to parameterize this surface. Okay, and then we also want to talk about the area of the surface. Okay, so let's go back to our spherical coordinates here. Okay, find the parametric representation of a sphere x squared plus y squared plus z squared equals a squared. Okay, so we have find the parametric representation of this guy. Okay, so x is equal to, okay, if we look at the sphere here, I'm going to look at the sphere instead of this guy. Okay, we've got our point on the sphere. Okay, and R. Okay, so we've got with radius A. So again, we've got a point on the sphere here. And so what do we have? We have a theta and a phi and and an A, which is our radius. So x is equal to A times the sine of phi times the cosine of theta. Or we'll just say sine is A cosine theta. Oops, sorry, cosine theta sine of phi. Okay, y is equal to A sine theta sine phi, and z is equal to A times the cosine of phi. Remember, this is phi. This thing is theta. Okay. Oh. Okay, and we know that phi goes from 0 to pi, and theta goes from 0 to 2 pi. Okay, the corresponding vector equation is r of theta phi is equal to a cosine theta sine phi I plus a sine theta sine phi j plus a cosine phi k. Okay, where the domain D is the rectangular domain 0 to pi, I'll say 0 to 2 pi by 0 to pi. Where phi are the circles of latitude, and theta are the circles of longitude. Okay, or should say the meridians of longitude. Okay, the meridians of longitude. Okay. Which are great circles. These are great circles. Okay, so what is that meaning? Well, it means if we took a globe, we wanted to know what's this angle phi here. Let me go down a little bit more. Okay, what's this angle phi here? Okay, that would produce on the globe. That would produce, okay, a circle of latitude. Okay, that's a circle of latitude. And tell me how far down. Okay, so phi of 90 degrees would be the equator, basically. Okay, that tells me how far down I went. Okay, whereas if we had a theta, okay, say that okay, say that this is my theta here. Okay, what does that tell me? That tells me where my great circle is. Okay, so I would get a great circle going through the poles and then back out again. So that tells me where my great circle is for longitude. So anyway, okay. So it's kind of counterintuitive, but it is what it is. Okay. Okay, number 2. Find a vector function that represents the elliptic paraboloid z equals x squared plus 2y squared. So we want to parameterize this, okay, and this is a three-dimensional figure. I'm going to parameterize this in 3 space, okay, using 2 variables. So this is r of x comma y is equal to, okay, well, we're going to parameterize this so that x is equal to x, y is equal to y, and z is equal to x squared plus 2y squared. So I want to say, okay, so r of xy is going to be equal to xi plus yj plus x squared plus 2y squared k. And that is my vector function in 2 variables, okay, for that elliptic parabola. Okay, so something like this. Okay, number 3. Find 2 different parametric representations of z equals the square root of x squared plus y squared. Okay. Interesting. Times 2, sorry. Put a 2 on the outside there. Okay, so A would be x equals x, y equals y, and z is equal to 2 radical x squared plus y squared. Okay, so that's one parametric representation. Okay, what would be another parametric representation? Well, if I divide by 2 and then square this thing, we get x squared plus y squared is equal to z squared over 4. Right? Okay. Okay, if we let x squared plus y squared equal r squared, right, then we can see that r is equal to z over 2. Where z is equal to 2r. So we could also see, based on this, that what would x be? Well, x would be r cosine theta, and y would be equal to r sine theta. Okay, putting that in polar coordinates. So we could write this in terms of r and theta, parameterize this thing in terms of r and theta, and we could say that that x is equal to r cosine theta, y is equal to r sine theta, and z is equal to 2r. Okay, so okay, if I wanted to write this as a vector valued function, I could say up here for a, r of xy is equal to xi plus yj plus 2 square root of x squared plus y squared k. Okay, so that's the first one. We could have r in terms of x and y, or we could have r in terms of r and theta. okay, r being the vector, the vector valued function r, not r for radius, but r for the vector value function. Okay, r in terms of r and theta, different r's here. Okay, which is equal to r cosine theta I, r sine theta j, plus 2rk. So parametrized two different ways. R is our vector field. Okay. Surfaces of revolution. Okay, so you deal with a little bit of this in Calc 1. Well, actually Calc 2. Okay, we do surfaces of revolution. Okay, so let's see what we can do with this thing. Okay, consider the surface S obtained by rotating the curve y equals f of x about the x-axis. Okay, so I have some sort of function being rotated, okay, about the x-axis. Okay. If there should be x, y, and this is z. Okay, if x, y, and z is a point on S, on the surface S, then we can parameterize this as x equals x, y equals f of x cosine theta, and z is equal to f of x sine theta. Okay, we can parameterize that in. And that, so x is x, okay, y, okay, is f of x cosine theta. Not like my drawing here. Go down. Okay, so we take that and we revolve it. Okay, about the x-axis. I don't know, I still don't like my drawing. It's kind of messing with my brain. I'm going to redraw it. Because we have, this is x, and this is y, and this is a function. Okay. Now we're going to rotate that around. Okay, and rotate this. About the x-axis. Okay, so we get this kind of surfacey thing. Okay, so we rotate it about the x-axis. Okay, so x is x. That's right. Okay, so where we are on this surface, let me highlight the surface. It didn't work. Let's highlight the surface here. Okay, so we have a point on the surface. Okay, x, y, and z. And then, what do we got here? And we're rotating through an angle, theta, right? So we're rotating through this angle, theta. Oh my gosh, come back to me. Stop. Could you just behave, please? Oops. Question. There we go. Okay, so we've got this angle, theta. Okay, so x is x. Okay, and y is going to be f of x. And then where are we on that? Yeah, due to the value, right? Yeah, y is dependent upon theta, and z is also dependent upon theta. Z and y. Yeah, how far out we are depends on theta in the y direction, and how far up we are in the z. Yeah, that makes sense. Cosine theta, sine theta. Yeah. Okay. That's good. Okay. So for services of revolution, we use that. Okay. So number 4, find the parametric equations for the surface generated by rotating y equals sine x about the x-axis. Okay, find the parametric equations that are going to generate that. Okay, well, okay, so x is equal to x, right? And y is going to be equal to f of x, which is sine of x, times the cosine of theta, okay? And z is equal to sine x sine theta, okay, where what? Where x has a restriction of 0 to 2 pi, and theta also has a same restriction. Why does x have that restriction? Because it's coming to us from the sine function. Okay, so, okay, and if we wanted a vector valued function for this, we would say this is a vector valued function on x and theta. Okay, is going to be equal to xi plus sine x cosine theta j plus sine x sine theta k. So this is 0 is less than or equal to theta, which is less than or equal to 2 pi. Okay, okay, let's talk about tangent planes. Tangent planes. Okay, the tangent plane to a surface. Okay, so we have this surface, and then we have a point, and then we have a plane that's tangent to the surface at that point. Okay, to the surface that contains the tangent vectors are u equaling dx du, partial x, partial u, of u naught v naught I, plus dy du, with an r, by the way. Okay, that's a v. Okay, u. Okay. Well, how many u's have we like that? It's just so they don't look like these. Okay. And this is a u naught plus partial of v with respect to u. Okay, u or u naught v naught. Okay. There's a j here and a k there. Okay. R of v, r sub v is partial x partial v of u naught I plus partial of y with respect to v u naught j plus the partial of z with respect to v of u naught k. Okay. So it contains the tangent vectors. Okay, so it contains these are the tangent vectors. Okay, tangent vectors. Okay, so tangent plane that contains these tangent vectors. So you have say a tangent vector and a tangent vector right, in the u direction and the v direction. Okay. So tangent vectors, and where RU cross RV is a normal vector to the tangent plane. Okay, so that's the normal vector to the tangent plane. Okay, I'll just call that n. Okay, n is equal to RU cross RV. Okay. Okay. So number 5. Find the tangent plane to the surface x equals u squared, y equals v squared, z equals u plus 2v at the point 113. Okay, so find the tangent plane to the surface of this. Okay, surface of this parametric equation, right? So this is some surface in parametric form. Okay, using u's and v's. And what are we going to say? Well, we say, well, r of u is equal to the partial of x with respect to u. Okay, so the partial of x with respect to u is going to be 2u, I, plus the partial on y with respect to u. Well, that's just 0, because there is no u. That's just uv, right? Okay, it's just 0j, plus, and then this is going to be just 1k. So 1 okay, is equal to 2uj plus k. Okay. Okay, RV, okay, is equal to, okay, 0 I plus 2.
Professor, isn't it 2UI?
Oh, yeah, thank you. It is 2, thank you. Okay, 2ui. So this is 0I plus 2vj plus 2k, which is equal to vj plus 2k. Okay, so let's do the cross product of this. Okay, RU cross RV, okay, IJK, we have 2U, 0, 1, 0, 2V, and 2. Okay, so what's this going to be equal to? This is going to be equal to cross product of this 0 minus 2V, so minus 2VI. Okay, plus, okay, this is going to be 4 minus 0, that's 4u. 4u minus 0 times 1 is 0. So that's j, 4j. I'm sorry, it's a minus. Okay, and then plus, this is just going to be 4uv. 4uv. Okay. 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 So this is the normal vector. Okay, the normal vector, right? So that's the normal vector. So I'm going to write this as n is equal to -2, sorry, that's v. Okay, -4u and 4uv. Okay. Okay, let me think about this for a second. So if x equals u squared, right? X equals u squared. Oh, then at 1, 1, 3, what is u equal to? Well, then at 1, 1, 3, x equals 1. So this implies that 1 is equal to u squared, which implies that 1 is equal to u. Okay, plus or minus u, right? Or plus or minus 1. Okay, so u is equal to plus or minus 1. Okay. Okay, likewise, if y is equal to v squared, then plus or minus 1 is equal to v, right? By the same logic. Okay. However, z is equal to z is equal to u plus 2v, right? So z is equal to u plus 2v. And so we know that's equal to 3. Okay, and so the only way that we could get 3 here is if u is equal to 1 and v is equal to 1. That's the only way that we would get positive 3, right? So we've isolated what u and v have to be equal to. So I can plug those back in for my normal vector. And I can say, my normal vector to my tangent plane has to be equal to -2 times 1, minus 4 times 1, and 4 times 1 times 1. So this is n is equal to -2, -4, and 4. Okay, but my original point, okay, because I'll call this P naught, is equal to 1, 1, 3, which means that R naught is equal to 1, 1, 3. And so we can use the equation of a plane, its normal vector and its point, the point in the normal vector, and we just say, oh, okay, well, this is going to be a times x minus x naught plus b times y minus y naught plus c times z minus z naught is equal to 0. And so the a refers to the normal vector, okay, and x, y, z. I didn't even have to do this, it's fine. Okay, so this is a, b, and c of my normal vector. So this is negative 2 x minus 1 plus negative 4 times y minus 1 plus 4 times z minus 3 is equal to 0. Okay, distribute. I get negative 2x plus 2, negative 4y plus 4, and 4z minus 12 is equal to 0. Okay, so this is going to give me negative 6. Okay, and so I'm going to say that this is negative 2x minus 4y plus 4z minus 6 equals 0. I could divide everything through by negative 2. And now we get x plus 2y minus 4z. No, sorry, it's 2. Minus 2z. Okay, plus 3 is equal to 0. You can keep the 3 on this side, or you could toss the other side. It really doesn't matter. X plus 2y minus 2z equal to negative 3. Okay. Okay, let's talk about surface area. If a smooth parametric surface S is given by the equation R of uv is equal to x of uv I plus y of uv j plus z of uv k. Just think of x, y, z in terms of some other parameter, 2 parameters. Right? We've got 3 parameters, 3 variables, but they're defined by 2 parameters. Okay, maybe it's r theta, maybe it's s and t, maybe it's u and v, however you want to think about it. Okay, but this is some vector valued function. Okay, but it's kind of like the chain rule, right? Where you take x in terms of uv, y in terms of uv, and z in terms of uv. Okay, where uv, u and v are elements of some domain D. Okay, and then the surface S is, okay, the surface area. The surface area of S is A of S is equal to the double integral over the domain of the magnitude of RU cross RV dA. Okay, so that's the magnitude of that thing. Okay. Okay, where what? Where RU is equal to the partial of x with respect to u, I, plus the partial of y with respect to u, j, plus the partial of z with respect to u, k, okay, and rv is equal to partial x with respect to v, I, partial of y with respect to v, j, and the partial of z with respect to v, k. Okay. For the special case, where z equals f of x, y, where x, y lies in D, and f has continuous partial derivatives, then, okay, we would say x equal to x, y is equal to y, and z is equal to f of x, y, right? Okay, we could parameterize it like that. Okay, and so so we would find the magnitude of this thing. Okay, so let me think about this for a second. Okay, so we want a cross product RU and RV. Okay, so what is, okay, so if we were to parameterize this in terms of x, y, it's only going to be parameterized in terms of x and y now, right? So x goes to x, y goes to y, and z goes to something in terms of x's and y's. F of x, y. Okay, so we can think of this, maybe I won't do this. Maybe I will just, it's getting a little confusing in a way, but what if I did it like this? What do I say, hey, look, let x be u, let y be v, and let z be in terms of u and v. Okay, then we can kind of make sense of this, I'm thinking.
You're such a liar.
So what would RU be? RU would be dx du. Well, that's just one. That's just I. Okay, plus, okay, dy du. Well, that's just 0. And then dz du. Well, that's just df du. It's just df du. Okay, so partial of f, partial of u. Okay. This is j plus k. Okay, and then what's RV? RV is 0i plus j plus partial of f partial of v. Okay, right? Partial of v partial of f partial of v. Okay. 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 So now what happens when we do the cross product of this? IJK business. So this is I. This is 1, 0, and the partial of f partial of u. This is 0, 1, partial of f partial of v. Okay, so when we do I, we're going to get negative, looks like negative df du. So negative df du, I, right? Minus, what's this one going to become? This is going to be negative df dv. right? It would be positive, but it's the negative. So negative df dv, so negative over the negative. Nope, it's just, it's the negative of, yeah, df dv. So df dv, okay. And then what would the k be? K would just be 1, looks like. Okay, plus 1. Okay. Okay, and this is J and this is K, right? Okay, so that's the cross of that. Okay, so if we think about this as negative df du and negative df dv and 1. Okay, now how will we find the magnitude of that? Find the magnitude of this. It's just it's the square root of each item squared, right? The square root of each item squared. Okay, so the magnitude of this vector, three-dimensional vector, is going to be negative df du squared plus negative df dv squared plus 1 squared. Okay, so that's the magnitude of that thing. We'll take the magnitude of that. Okay, vector. Okay, so I'm going to rewrite this a little bit. I'm going to say that this is the square root of 1 minus, or 1 plus df du squared, okay, plus df df dv squared, okay. But I used u and v as kind of a dummy variable here, right? What was u? Wasn't u just originally x, right? Wasn't u just x and y was v? Okay, so let's say that, and what was f? F was equal to z. Okay, f was equal to z. So I'm going to sub back in and just say, oh, this is 1 plus dz dx squared plus dz dy squared. Okay, which is very similar. Okay, right? And what is this going to be equal to? The double integral over d of as, right? So that's what this thing is equal to for the very special case when we have a z equals some function of x and y, then this comes out to looking like this, which is very similar. Think of this as my surface area formula. Okay, this is a surface area formula for a surface z equals some f of x, y, right? So think of this like we've got some sort of sheet, okay, some sort of sheet, and we want to find the surface area of this thing, right? What's the surface area of this thing? Well, no, it's just the projection of this sheet onto the xy plane, right? In some sort of D, some sort of domain, okay? Projects down onto this D, okay? And so in that domain, projecting onto the xy plane, okay, we get this, okay? And we're gonna take the double integral of that D, this is dA with respect to, sorry, dA, and this would be in terms of just dx dy, right? Okay. Okay, which is extremely analogous to what we did for our arc length, right? Arc length. What was our arc length formula? Well, our arc length formula was a to b of the square root of 1 plus dy dx squared. Well, look at that. Don't those look fairly similar? We have an arc length formula, okay, L, in basically one dimension, right? And okay, in 2 dimensions, basically, you could say. Arc length in 2 dimensions is very analogous to the surface area in 3 dimensions. That's kind of cool. Okay. Okay. So number 6 here. Find the surface area. Surface area of the paraboloid z equals x squared plus y squared that lies under the plane z equals 9. Okay, so what do we got? We got this paraboloid here, okay, that z equals 9. Oops. Okay, so we got this paraboloid, and we're at z equals 9, okay? Okay, so at z equals 9, what is the domain that's this shadow here? What's the shadow of the domain here? Well, wouldn't that be a circle? And what would, when z is equal to 9, then z is also equal to x squared plus y squared. Okay, so then isn't that just a circle of radius 3? Right, so what's the domain here? The domain is this circle of radius 3. Of radius 3 at 0, 0, right? So it's centered at 0, 0. Oh, okay. So that is my domain. My domain is basically that there. So it would be not necessarily the circle, but it would be the disk. I say the disk of radius 3 centered, because we want everything in between, right? So basically, x squared plus y squared is less than or equal to 9. That's my domain. Right? Okay. Okay. So let's figure out what we need to do here. Well, let's find the area here. The area, okay, is going to be equal to, okay, we want the surface area of this thing, right? Surface area. Okay, surface area of this thing is equal to, okay, over d of the square root of 1 plus dz dx squared plus dz dy squared. Okay, so the partial with respect to z, okay, with respect to x. Okay, well, z was equal to x squared plus y squared. So the partial of z with respect to x, that's just 2x. Okay, partial z with respect to x is 2x. Okay, and what's the partial z with respect to y? Well, that's just 2y. Okay. So we're going to say this is d, okay, of the square root of 1 plus 2x squared plus 2y squared dy dx. Okay. Nice. Okay. However, okay, notice what the domain is. The domain is a circle, right? It is a circle. So we will want to change this to polar coordinates. So let's change this to polar coordinates. Let's let x equal r cosine theta and y equal r sine theta. Okay. Okay, and so we're going to say that, because what's our domain? Our domain is this circle, right? Okay, circle of radius 3. Okay, so we're going to say, well, this is going to be, okay, the integral of the square root of 1 plus r cosine theta, or sorry, 2r cosine theta squared, okay, plus 2r sine theta squared. Okay, r, don't forget the r dr d theta, where r goes from 0 to 3 and theta goes from 0 to 2 pi. Okay, nice. Okay, so now we're going to go from 0 to 2 pi and 0 to 3. This is going to be the square root of 1 plus 4r squared cosine squared theta plus 4r squared sine squared theta. I'm going to put the r in front, and then dr d theta. So 0 to 2 pi, 0 to 3 of r times, now if I were to factor out the 4r squared, could you see that if I pulled out the 4r squared, I'd be left with 1, because cosine plus sine, cosine squared plus sine squared is just 1. All right, so this really just becomes 1 plus 4r squared dr d theta. Okay, so now what we want to do is we want to do a u sub. U is equal to 1 plus 4r squared. Du is equal to 8r dr. So divide by 8, and we get our r dr. So that's good. Okay. So then we're going to integrate. We have the square root of u, the square root of u over 8. Okay. So that's u to the 1/2. So when I integrate that, I'm going to get 2/3 u to the 3/2 over 8. Okay, and then I'm going to plug in my original value here, just because I want to keep my original limits of integration. So, I mean, I could change them. I guess I could change them here. What are my limits now? So plug in 0, we get 1. Plug in 3, we get what? What do we get if we plug in 3? We get 37, I think. Is that right? Yeah, 37. Okay, so what's this going to be? This is going to be, it becomes 4. So we get 37 to the 3/2 over 12 minus 1 to the 3/2 over 12. Okay, I could factor out the 1/12, and I get 37 radical 37 minus 1 radical 1, which is just 1. 7, 1, and then we want to integrate that from 0 to 2 pi on d theta. This has no thetas at all, so it's just going to be 2 pi over 12 times 37 radical 37 minus 1, and this is just pi over 6, 37 radical 37 minus 1. That's it. Okay, that was the surface area for that elliptic paraboloid. And you could have done this, I mean, sort of. You could have done this problem using Calc 2 techniques if you really wanted to. Okay, you could think of it as taking this curve here, or actually taking this curve here and rotating it around the y-axis, finding the surface of revolution. Okay, if you really wanted to, you would get the exact same answer. Okay, but we know better. We know better than that. Okay, let's jump into 16.7. Okay, we may not finish it today, but I'd like to at least jump there. I got off track here. Does anybody need this? Is everybody good? This one? Good. Okay, well you have the video anyway. Okay, come on, come back to me. Where are you? There's the paper. Square up the paper. Okay, so 16.7. Okay, surface integrals. Okay, analogous to line integrals. Okay, analogous to line integrals. So instead of doing a line integral, okay, now we're doing a surface integral. Okay, so taking the integral over a line, okay, versus taking the integral over a surface. Okay, okay, so, right, whereas before, okay, we had our line integrals. This goes all the way back to 16.2. Okay, so where we said that we had c f of x, y, ds, okay, was equal to a to b of f of x of t, y of t, times the square root. Okay, this is a line integral. Square root dx dt squared plus dy dt squared. Okay, dt. Okay, so this was a line integral that we established way back in 16.2. Okay, so we're gonna take this analogy, okay, and we're just gonna say we're gonna generalize it, make it even more general, okay, but then we're gonna bring it back to this guy here, okay, and see, well, what's happening. So the surface integral, okay, the surface integral of f over the surface S is given to us as the double integral of S over f of x, y, z ds now, where S is capital S. Okay, lowercase s for 2 dimensions, capital S for 3 dimensions. Okay, let's keep that in mind. Okay, so it's the only way we can keep track of, is it a 2-dimensional thing or is it a 3-dimensional thing? Is just whether it's lowercase s or uppercase s, because you could have x squared plus y squared, and you'd be like, well, is that, is equal to 3, and you're like, well, is that a 2-dimensional or is that a 3-dimensional? And you're like, oh, you wouldn't know because it could be 3-dimensional, because you would just say that it's 0z, right? 0z squared or something plus 3. You just wouldn't know. You wouldn't know if it goes off in z in infinite direction or if it doesn't even have a z component. Okay, so let's keep that in mind. Okay, this is equal to the double integral over the 2-dimensional domain of f of r of uv. So we parameterize this thing in terms of r uv. Okay, when the magnitude of ru cross rv, okay, dA, okay, over the area of the surface interval. Okay, with respect to A. Instead of before we had dt, because t was just one parameter. Now it's in terms of two parameters, u and v, and so it's an area, okay, of u versus v. Okay, and whereas before we had a single integral, now we have a double integral. Okay, if again z is equal to g of xy is the surface. Okay, this is kind of like the trivial case, right? With parametric equations, or we wouldn't say trivial case, I'd say standard case. So we're at the standard case. Okay, where z is equal to something in terms of x and y, we could solve for c. It's a function of x, y, right? Then we could say x equals x, y equals y, and z equals g of xy. Then, okay, we can say that this thing, okay, the surface integral of f of x, y, z ds is equal to the double integral of d of f of x, y, g of xy, okay, times the square root of this thing. But we saw that this thing was just a of s. It was just a of s, right? And we said that, well, a of s, when it was that, was equal to what? It was equal to the square root of 1 plus dz, but in this case, z is, oh, we could say z, that's fine. Z is just g. So it could be the partial of g with respect to x, okay? So we could do dz over dx squared plus the partial of z with respect to y squared, okay, dA. Okay, so that's that. If we have something that's solved for z, then this thing is my surface integral. That's my surface integral there. Okay. Okay. Therefore, let's do a problem here. Evaluate, okay, the surface integral y ds, okay, ds. See, again, we don't know, is this going to be 2 dimensions, 3 dimensions? I mean, we do know that it's 3 dimensions because it's got a double integral, but we just use that capital S to designate, hey, it's 3, it's y, but it's in 3 dimensions, okay? So, okay. So where S is the surface, where S is the surface, okay, z is equal to x plus y squared, where x goes from 0 to 1 and y goes from 0 to 2. We're going to take the surface integral of this thing, y ds, and we're going to say, this thing is going to be, okay, over the domain d of y, okay, so this is y, f of x, y, g, z. I didn't have to change anything there. So this is, I mean, I could write the whole thing over again, x, y, g of x, y, right? So, but what is that? That's just y. That's just y. It's just y. Okay, it's just y times the square root of 1 plus dz dx squared plus dz dy squared dA. Okay, so now let's see what we got here. Okay, so that's the surface that I'm looking over. Let's do this. So what is dz dx? What is this with respect to x? Well, it's just 1, right? It's just 1. Okay, and then what is dz dy? Well, that's just 2y. Okay, so interesting. So what is this going to be? This is going to be my domain. What is my domain? My domain is going to go, x's are going to go from 0 to 1, and y's are going to go from 0 to 2. Okay. So this is y times the square root of 1 plus 1 squared plus 2y squared, and then this is going to be dy dx. Oh, okay. So we've got y times the square root. This is going to be 1 plus 1, which is 2. That's 2 plus, this is going to be 4y squared. Okay, dy dx from 0 to 2, 0 to 1. Okay, let's do a u sub on this. U is equal to 2 plus 4y squared. So u is equal to 8y dy. So divide by 8. And look at that. We've got our y dy. That's nice. And so u over 8 is equal to y dy. Okay. So then we've got u to the 1/2. Right? U to the 1/2. We're going to integrate that. Sorry, this is du over 8. U to the 1/2 du over 8. Integrate from, we could plug this in. What are the limits here? The limits are going to go the 2, I think. 2. Yeah, 2 and 18, I think. Plug that in. We get 16, yeah, 18. Okay. So this is going to be 1/8 times the square root of 18 minus the square root of 2. So, and then that's just the y's. Okay, there are no x's in this problem. So we're pretty much there. The x's go from 0 to 1, right? 18. That's actually, I can actually simplify this even more. This is 3, this is 9 times 2, so this is 3 radical 2 minus radical 2. Look at that. That's kind of cool. No, this is wrong. I'm wrong. I did this wrong. How did I do this wrong? I didn't integrate. That's how I did this wrong. This is 2 to 18. So this is 2/3 u to the 3/2 times 1/8 evaluated from 2 to 18. There we go. Missing something. Okay, so this is going to be, once again, 1/12 times, this is going to be 18 to the 3/2 minus 2 to the 3/2. Okay. So this is 18 radical 18 minus 2 radical 2. Okay, so this is going to be 18 times 3 radical 2 minus 2 radical 2. That's 54. 54 radical 2 minus 2 radical 2 is 52 radical 2 over 12. Okay, which is going to end up being divided by top by bottom by 4. That's 13 radical 2 over 3, I believe. Okay, so now I'm going to want to integrate that from 0 to 1 dx. There's no x's, just a number. So this is just 13 radical 2 over 3x evaluated from 0 to 1. Plug in 1, we get the same thing, 13 radical 2 over 3. I don't know why I keep going off the page. Who knows? Whatever. I'll just stay off the page.
Can you scroll up just a bit, please?
Sure.
Thank you.
Okay, we good? Okay, number 2. Let's compute the surface integral s x squared ds, where, oh, this is going to be fun, where S is the unit sphere. Boom. Okay, unit sphere. What's the unit sphere? X squared plus y squared. X squared plus y squared plus z squared equals 1. That's great. Okay, so let's parametrize with spherical coordinates. Okay, let's parametrize this with spherical coordinates. Okay, so in this case, we can't solve directly for z. Does that make sense? If we could solve directly for z, then we could do the same thing that we did before. But we cannot solve directly for z because it's not a function. Okay, and so we're kind of screwed, and we have to use the previous example or the previous formula, which is way up here. Okay, I could scroll over. Okay, we have to use this thing here. Okay, so we have to get this in terms of other variables, like, you know, the unit sphere is going to be in terms of theta and, you know, r theta and, well, theta and phi. It's going to be in terms of theta and phi. And then we're going to have to do the cross product, find the magnitude of that, and then integrate. Okay, so fun stuff. Okay, so let's parametrize this. Okay, so we're going to say that x is equal to, okay, r. Well, I mean, you could, I don't know, it's not really r, but it was just a unit sphere. The surface is the unit sphere. So it's the sphere, unit sphere, that's the surface. So how would we parametrize the unit sphere? It's the same thing the way that we parametrize the unit circle, but we're using spherical coordinates. So, you know, in the unit sphere, rho is equal to 1. Remember rho? Rho that I can't, rho is equal to 1. So you said, oh, rho times the cosine of theta sine phi, y equals rho times the sine of theta sine phi, and z is equal to rho times the cosine of phi. Well, rho is equal to 1 here. Okay, so you don't have to worry about it. Okay, it's not r squared, it's just 1. So x is equal to just cosine theta sine phi, y equals sine theta sine phi, and z is equal to cosine phi. So those are my parameters. Okay. So okay, so what would r of theta look like? Okay, so r of theta, okay, would be equal to dx d theta I, dy d theta j, dz d theta k. Okay. So what we got here? Well, dx d theta, okay, is integrate this on theta. So the integral of cosine is negative sine. So this is going to be negative sine theta. Sorry, the derivative of cosine is negative sine. This is negative sine theta sine phi, right? Sine phi I. Okay. Plus on y, this is going to be cosine theta sine phi, cosine theta sine phi j. I'm not doing the right. Sine phi j. Okay, plus, and then, well, there is nothing on theta for z. It's just phis. So that's 0 k. So that's what that one is. What about r of phi? R of phi. Well, again, that's just dx d phi, dy d phi, dz d phi, right? So dx d phi is going to be cosine phi cosine theta I, okay, plus y is going to be, this is going to be cosine theta sine, sorry, cosine phi sine theta j, and the cosine phi, that's negative sine phi, so this is minus sine phi k. Okay, so now what are we going to have to do? We're going to have to find the magnitude of the cross product of this thing. So let's cross this thing first. So r theta cross r phi. Okay, let's cross product this thing. Bad boy here. Okay, I, j, k. And so we're going to say, oh, this is negative sine phi. This is cosine theta sine phi, and that's 0. And then we have cosine phi cosine theta, cosine phi sine theta, and negative sine phi. Okay, so let's cross product this thing. Ooh, fun stuff, I tell you. Whoosh. Okay, so I, what's going to be for I? Well, it's going to be this thing here. Cosine, this is going to be negative. Okay, all right. I'm missing a negative somewhere. No? Okay, well, whatever. Okay, so cross off row and column, and we get this determinant. Well, this is, should we? I don't know. We'll see what happens. Okay, this is negative. It really doesn't matter. They're all negatives. They're going to get squared anyway in the end. Okay, so this is sine, this is cosine theta sine squared phi. Cosine theta sine squared phi. Okay, I. A minus what? Cross off row and column here. Minus sine squared phi sine theta. Did I screw this up? What's the first one? The first one was cosine. Oh, this is a phi. Sorry. Let's try to keep these all in order. Okay, this is going to be sine theta sine squared phi. Okay. Minus. Okay. For j, cross off wrong column. That's just 0, right? Minus 0. Okay, j. Okay, and then k. Yeah. And then k, cross off wrong column there. So for k, we get cosine theta sine, no, sorry, that's a phi. Cosine phi. So we've got negative sine squared theta, negative sine squared theta, and then sine phi cosine phi, sine phi cosine phi, okay, minus, okay, and then this is going to be cosine squared theta, Okay, cosine squared theta. And then again, it's a sine phi, cosine phi. Sine phi, cosine phi. Okay, okay. So now this is just negative cosine theta sine squared phi I. Okay, this is going to be minus sine theta sine squared phi j. This I could factor out the sine. This is just a minus. I could factor out a negative. I could factor out the sine phi cosine phi, and that leaves me with a sine squared theta plus cosine squared theta, which goes to 1. Okay. Okay, looks good. Okay, so now what I'm going to do, I'm going to take the square root of this. Okay, so that's my cross product. And then to find the magnitude of this, I'm going to take the cross product of this. I already took the cross product. I'm going to take the magnitude of this and square these things. So this becomes negative cosine theta sine squared phi squared plus negative sine theta sine squared phi squared. Okay, plus negative sine phi cosine phi squared. Okay, so this becomes cosine squared theta sine to the 4th phi minus or plus sine squared theta sine to the 4th phi plus sine squared phi cosine squared phi. Okay. So factor out the sine to the 4th phi. So sine to the 4th phi times cosine squared theta plus sine squared theta plus sine squared phi cosine squared phi. Nice, 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 nice. Okay. And so what are we going to get here? This goes to 1. And then I'm going to do something sneaky here. I'm going to factor out a sine squared out of both of these. So that's a sine squared phi times sine squared phi plus cosine squared phi. So that's another 1. That's nice. And so, yeah, so then I'm just going to take the square root of that, right? Because this is all square rooted. And so this ends up being the absolute value of sine phi. Okay. However, where is phi designated? Phi is only designated from 0 to the pi, right? Isn't phi only designated from 0 to pi? So what are my y values from 0 to pi? Well, aren't they always positive? So this implies that it's just sine of phi, right? Sine phi is always greater than 0. Okay, so nice. So I can get rid of the absolute value bars. That's all they really want to do anyway. Okay, so when we go back to our original here, right, we say that, what do we want? We wanted this double integral, right? Okay, in terms of, okay, we want to parameterize this thing, blah, 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 and we want to turn this thing, okay, into a double integral, okay, that involves, okay, f of r of uv, but in this case it's theta and phi, R theta and phi, and then R of theta cross R of phi dA. Okay, dA. Okay, so try to see what's going on here. Okay, so what was the original? The original one was we wanted x squared ds, right? So we wanted, the original was s x squared ds. Okay, and so we said we went through that whole work to find out that this thing was just sine phi. That was it. Boom. That was fun. Okay, and what's x? Well, what is x? What did we say x was? X was equal to, okay, x was equal to, so this thing, I didn't really want to erase that. Let me put it back. Okay. So x is equal to, in terms of theta and phi, we said that x was equal to sine phi cosine theta. Sine phi cosine theta. Okay. Okay, so that's good. Okay. So now we're going to say that this thing operates, okay, this thing's squared, right? X squared would be that squared. So this is going to be sine squared phi cosine squared theta, okay? But we've got an extra sine theta, or sine phi, and then d phi d theta, okay? So, okay. So, and then this goes, what does phi go from? Phi goes from 0 to pi, and theta goes from 0 to 2 pi. Okay. Okay, so this kind of helps to see where that integration factor came from. Remember what we had when we said when we integrate with respect to spherical coordinates, we have to have that integration factor of rho squared sine phi, right? And we're like, where the hell did that come from? Well, this is where it comes from. Okay, our rho in this case is 1. Okay, if we had a rho that was a rho, we would end up with a rho squared here. Okay, so keep that in mind. Okay, but our rho was 1 in this case because it was the unit sphere and not just some generic sphere in spherical coordinates. But that was our integration factor, and that shows up right here. Okay, so we just kind of derived spherical coordinates there. Okay, so let's integrate this. Okay, let's integrate. This is going to be sine cubed, right? Sine cubed phi. Okay, from 0 to pi d phi, and then I can pull the cosine squared theta out from 0 to 2 pi d theta. I can kind of integrate these. They're basically separable at this point. So sine cubed, okay, so sine cubed is going to be sine of phi times sine squared of phi. Okay, so I'm going to split off a sine, and then I'm going to change. Okay, I'm going to change this into 1 minus cosine squared phi. Okay, and then sine phi. Okay, so I can change the sine into cosine so I can get an integration factor. Okay, so 0 to pi, we're still doing 0 to pi's here, d phi. Okay, so u is going to be equal to, what do I want u to be equal to? I want u to be equal to just cosine of phi. Cosine phi. So du is equal to negative sine phi d phi. So that's negative du equals sine phi d phi. Okay. So okay. So now, what do I get? I get the, well, what's the cosine of 0? That's 1, right? So I'll do that in a second. So 1 to, cosine of pi is negative 1. So that's 1 to negative 1 of 1 minus u squared, but then we have a negative du. Okay, so that's going to kind of flip this around, but that's also going to flip this around. If I flip this around, I would cancel out that negative. If I went negative 1 to 1, I could cancel that negative out. So just be 1 minus u squared du. Okay, so this is going to be u minus u cubed over 3 from negative 1 to 1. So this is 1 minus 1/3, right? Minus 1/3 minus negative 1 minus negative 1/3. Okay, so that's interesting. Okay, so this is going to be, this is 2/3, and this is negative 2/3. So that's minus a negative 2/3, which is 4/3. Okay, so that's 4/3. Okay, so 4/3 is what I get from that. But now I want to integrate, okay, 0 to 2 pi of my theta, which was cosine squared theta. So we've got cosine squared theta d theta. Okay, and this I'm going to change into 1 plus cosine 2 theta. I'm going to use that half angle identity over 2. I'm going to pull out the 1/2. So this becomes 2/3, 0 to 2 pi of 1 plus cosine 2 theta d theta. Okay, so this thing, we've done this many, many times in this class, but this thing is going to go to sines. And when you plug in sine of 0, you get 0, and sine of, I'll just do it. It's just u is equal to 2 theta. Okay, du is equal to 2d theta. Okay, and so we get over 2, right? And then we just say this is 0, 0 to 4 pi, 0 to 4 pi of, is that right? Can I do that? 1 plus, no, I don't think I can do that. I need to separate this. It's 2/3 times 0 to 2 pi of 1 d theta plus 0 to 2 pi of cosine 2 theta d theta. Okay, and so then it's 2/3. This is theta evaluated from 0 to 2 pi, which is just going to be 4 pi over 3, plus this thing is just going to be 1/2. Integrate this. This is sine of 2 theta, right? Okay, evaluated from 0 to 2 pi. Okay, so I guess that's where you get the 4 pi from. But what is this thing going to go? This thing's just going to go to 0. Okay, so the answer is 4 pi over 3. Okay. Okay, so let's talk about orientable surfaces. Okay, These are two-sided surfaces. Okay, so say that we're going around this thing, right? But we have this surface. Oh, didn't do so well. We have this surface here. Okay, think of it like a top half of a dome. Okay, but and C, remember C is our closed bounded. Okay, and C is our line integral. D is our domain. D is our domain. But now we have this, we would say this is upward orientation. Okay, think about the right-hand rule, right? Right-hand rule. Okay, so going around C, we're going up, upward orientation. Okay. Okay, which really comes, like the curl comes to us from that idea as well. I did find this online. If you're interested in doing more, being better at understanding the engineering application of divergence and curl, I'm not going to go into it because I don't have time. But will you stop my share? Screen share, and then this, just the screen, just share my screen. Okay, I think it was called Imagine Math. Imagine Math. Imagine Math, something. It's on my phone. .com, I think. Let me look up on my phone real quick. Oh, Math Insight. That's what it's called. Math Insight. Okay, so this is Math Insight, right? So, okay. So, I don't know this. They have on here. Vector field. Okay, they have these applets, which are kind of cool. Don't want this. I want curl. Curl. Just show me curl. Here we go. There we go. Yeah, see, it has this, and it shows you kind of like in this vector field how this thing is related to curl, right? Curl is kind of like how this thing is. Think about fluid motion, and if you were to have a ball parallel to the z-axis, how would that ball be? That would be the curl. The curl is like how is that? So how is it making that ball spin? It's curling around that thing. And the same thing goes with divergence. Divergence is expanding and contracting. So it was just kind of a fun thing to look at. So it's called Math Insight. Math Insight. So you know, they have these little apps. So it's like, oh, it curls around that. It curls around, okay, in this fluid, okay, because this all comes to us from the fluid dynamics and stuff. So, and it gives you the idea behind Green's theorem. It's kind of interesting to go get into this stuff a little bit deeper. So look deeper, look deeper. So anyway, I just thought I'd pass that on to you. Okay, because we don't talk about the engineering application of this stuff so much. Okay, it all has to deal with fluid dynamics. Okay, so we say that S, okay, S, this thing is S, okay, has upward orientation, while C has positive orientation around D. Okay. Okay, so it's positively oriented surface. Okay. The surface integral of F over S with unit normal vector n, okay, where F is a vector field is the double integral of S F dot ds is equal to the double integral of S dot F dot n ds. Okay. Okay, so this is a vector field F. Okay. Okay, so which is equal to, okay, the double integral D of F dot RU cross RV dA. Okay, so this is a vector field that we can take this surface integral and turn it into a double integral. Okay. Okay, we say that the surface integral over F dot ds is equal to the surface integral of F dot n ds, okay, is called the flux. Okay, flux of the vector field. And again, I didn't have time to go into exactly what the flux is, but again, you can go onto Math Insight and read all that you want to read, okay, about how that relates to the fluid. Go away. Okay, how that relates to the fluid dynamics. Okay, so if we plug in flux here, okay. Okay, so flux. Okay, image. Oh, that's just an image. I don't need the image. Okay. Subtleties about divergence. Divergence is expanding and contracting. How fluid expands and contracts, that's divergence. So if it's positive, it's going in and kind of blowing up the ball. And if it's negative divergence, it's going out and it's air is leaving the ball. Okay. But there should be something about flux in here. Okay. Diagram illustration of flux molecules pointing down, the concentration gradient. I don't know either. Okay. Try to- oh, same thing. Okay. Nope. Yeah, I don't know. Forget it. At any rate. Okay. By parametrizing, okay, x equals x, y equals y, and z equals g of x, y. Then we could say that the surface integral of the vector field, okay, dot ds is equal to, okay, the double integral of negative p, okay, partial of g, which is z basically, we could say partial of z with respect to x, and I'll do z with respect to x, okay, minus q, partial z with respect to y, plus r, okay, and that's all dA. Okay. Okay, where f is equal to pi plus qj plus rk. Okay. Okay, I think that's it. I think we're good at this point. Okay. Okay, so I'll see you guys on Monday.
Bye.
You're welcome.
Professor, when would you upload this to your YouTube channel?
In about an hour.
Okay, perfect. Thank you.